We've mentioned in prior videos that sometimes there's more than one way of drawing a correct Lewis structure for a particle. We got to follow two rules, and we have to assign octets to everybody that needs an octet. Some elements can take it extended if they have d orbitals, and then we only have a certain amount of valence electrons to work with. So at the end we have to kind of make sure that our electron count is correct. But often you can draw more than one structure that would follow those rules. Formal charge is a way of determining which Lewis structure is most correct or most stable when more than one seems possible. So first we have to figure out how to assign something called a formal charge. It's not bad. You'll get really quick at this. Number one, you're going to look at all the atoms in your structure. It could be a neutral molecule, it could be a polyatomic ion, and for each atom in your structure, you want to determine the amount of valence electrons that atom would normally carry. So in the free atom, meaning like if it were not charged. So for example, like if I have oxygen in my structure, oxygen would normally carry 6 valence electrons. If I had fluorine would normally carry 7 valence electrons, and so on. So I'm going to look for the normal amount of valence electrons. Number two, I have to determine the amount of electrons that you've assigned to that atom in your structure. How many electrons belong to that atom in your molecule or polyatomic ion? So you're going to look for lone pairs. If there are any lone pairs of electrons, they belong entirely to that particular atom. Number two, if there are electrons shared in a bond, we're going to divide them equally between the two atoms in that bond. So for example, if I had a single bond, that's 2 electrons being shared. We're going to assign one of those electrons to each atom in the bond. If I had a triple bond, that's 6 electrons being shared. I'm going to split them equally and say there's 3 electrons for each of the 2 atoms. Now I know there could be some discrepancies in that method. If you had one atom with a high electronegativity, the electrons might not be divided equally in real life. But this is going to give us a good snapshot of which structures might be more stable. So in the end, I'm going to do a little subtraction. You're going to take the amount of valence electrons in the free atom that you'd normally find if you look at the trend on the periodic table and subtract the amount of electrons that you've assigned to that atom in your structure. We're going to do that for all atoms in the molecule or the ion. And then here's our rule for figuring out which is most stable. Number one, atoms in a molecule would like to have a formal charge as close to 0 as possible. And when we say they would like to have formal charges of 0, it means they're more stable that way. If you've assigned in your structure the amount of valence electrons you'd normally find in that particular atom, that's stable. So number one, I want to look for a structure that has a lot of formal charges that are 0 or as close to 0 as possible. Number two, if you have any negative formal charges, which could happen, they could end up being positive or negative, you want the negative formal charge to be on the atom with the highest electronegativity in that compound. Okay, that sounds fun. And we're going to look at examples of these rules. Number three, the sum of all formal charges should be 0, and this should obviously say if the molecule is neutral. If it's a polyatomic ion, the sum of the formal charges should equal the charge on that ion. Holy cow, that's a lot of rules, huh? Actually, you're going to really like this. It's kind of fun. Let's try one. Okay, so let's try the sulfate ion. First, we got to draw a Lewis structure, right? And often what you'll find on a free response question is they might say, like, draw at least 2 or 3 acceptable Lewis structures for the sulfate ion. That could be like part A. Then in part B, they'll say, use formal charge to determine which of your structures is the most stable, or something along those lines. There's a lot of different ways you can draw the sulfate ion. You don't have to come up with all of them on the AP test. They might just say, draw 2 acceptable structures, or something like that. Okay, so let's draw an acceptable structure, huh? if I try to follow the rules of Lewis structures, this one ends up being a little tricky, like to get started at least. Normally when I draw a sulfur, I want to draw a sulfur with his 6 valence electrons, and then it kind of looks like sulfur with like 2 bonds, right? He's got 2 lone pairs of electrons, 2 single electrons. So how the heck are you supposed to put on 4 oxygen, right? Okay, let's not follow the rules in this case. Instead, let's go to our second option. If being a rule follower doesn't seem to work at first glance, let's go with electron count. Okay, so normally sulfur would carry 6 valence electrons. 6 valence electrons. Oxygen would also carry 6 valence electrons, and there are 4. So if I add that up, I get a total of 30 electrons, but there's also a -2 charge, which means that this structure is only possible if I gain 2 electrons. So we're going to add 2 for a total of 32 electrons. So with 32 electrons, I should be able to come up with a structure that gives everybody at least an octet. Now, sulfur is in the 3rd energy level, which means d orbitals are a possibility, and I could go extended octet on the sulfur. So from here, you just try something. This is the fun part, right? You get to be a little creative. I don't know, let's not go too wacko. Let's just try some single bonds. Let's see if this works. Sulfur with 4 oxygen. Sulfur has an octet, which he needs at least an octet. And then the oxygens must have an octet with no exceptions. So we'll go around and give them some extra electrons. There we go. Everybody's got an octet. Now remember, we've always kind of said that covalent bonding is about sharing. It's about sharing all of the valence electrons available. So we don't have to start with this little, Lewis structure like what you may have done last year, where there's 2 singles and 2 pairs. Or it might look kind of strange that you have oxygens. Ooh, that's not how I drew oxygen last year, with a single bond and a bunch of lone pairs. But that's okay, If we gave everybody an octet and we used 32 electrons, this is an acceptable Lewis structure. 2, 4, 6, 8 times 4. Hey, I like it. This is acceptable. And now technically, we should put this in brackets because it's an ion. And then the charge -2 goes on the outside. This is only possible if we had 2 extra electrons. 30 electrons would not have been enough to give everybody an octet. All right, let's try another one. I don't know. Since sulfur can accept an extended octet, we can get a little creative with the sulfur. What if we did like a combo deal? What if we did like some double bond oxygens and some single oxygens? Ooh, sulfur's overloaded. I gave the sulfur 2, 4, 6, 8, 10, 12 electrons. Each of those bonds represents 2. But that's okay, because sulfur's in the 3rd energy level. There's d orbitals. The oxygen must have an octet with no exceptions. Cool. So we'll give him some extra electrons. There's your octet. 2, 4, 6, 8. 2, 4. Oh, see, too many. Did you catch me on that? Too many. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. This is acceptable. Oh boy, I drew it kind of close to the other one. -2. This is acceptable. This is totally fine. Now you could do a spin on this while we're thinking about it. What if it said draw 3 acceptable Lewis structures? And so you drew these 2, and then your 3rd structure looked kind of like this. What if you did something kind of like that? You've got 2 singles and 2 pairs, but on paper, you drew them in a little different arrangement. That's the same structure. Here's where you have to put on like your visual thinking cap a little bit. Same structure. We're trying to draw something that is really 3-dimensional, but we're drawing it flat like a pancake on paper. And in the next couple videos, we're going to look at those 3-dimensional shapes. You remember like the bent and the tetrahedron and all that fun stuff? In real life, these are the same structure. You've got 2 double bonded oxygens and 2 single bonds. How you draw it on paper might look a little different, but in 3 dimensions, these are really the same. So being a little careful, because sometimes people might lose points because they'll be like, oh, that was so easy. I just did a little different arrangement of the double bonds and single bonds, and I got my 3 different structures. But actually, you only have 2 different structures, the blue structure and the first red structure. Okay, so now if we had to come up with a third one, I really got to think of something different. And you could, let's go like really crazy. Let's go super crazy. And go like sulfur, watch this, single, double, triple. Now what do you want? I'm not going to do a quad bond. Somebody will always ask that. I don't know, let's go single. Do quad bonds even exist? Highly controversial. But let's look at something like this. The sulfur is nuts. But, I mean, it's okay for now, at least. This follows the rule. Sulfur does have available d orbitals, and he can take an extended octet. So now we got to finish off these oxygen with an octet. So we'll add extra electrons. You only need 1. Make sure everybody's got an octet. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6. Hey, this is interesting. Look at this wild thing. That's got 32 electrons. It follows the rules. Everybody's got an octet that needs an octet, meaning oxygen. And sulfur can take an extended. So here are 3 very different Lewis structures that are all acceptable. Now, you might have an idea in your head that the last one is probably not the real sulfur ion or sulfate ion. Let's find out. Here's how formal charge works. Okay, so for convenience, let's call this like oxygen A, B, C, D. Let's go, oops, I'll use a different color. Oxygen A, B, C, and D. And I'm going to do this to all of them. A, B, C, and D. And then let's call this oxygen A, B, C, and D. Okay, so we need to assign formal charges. Formal charge is this. Let's do sulfur. The number of valence electrons that sulfur would normally carry on the periodic table, 6. Then we're going to subtract the amount of electrons that we've assigned in our structure. In this first structure, I've got single bonds on all those oxygens, which count as 2 electrons being shared. We're going to share those 2 equally between the sulfur and the oxygen. So realistically, if there are right now 8 electrons on sulfur, only 4 of them are going to belong to sulfur. And you can't see this, but I'm doing air quotes right now. Belong to sulfur. We take the electrons that are shared in the bond and we split them equally between the 2 atoms. So 1 electron goes to oxygen, 1 electron goes to sulfur. So in these single bonds, sulfur has 4 electrons total. There are 4 single bonds, which would add up to 8 total electrons. Half go to sulfur, the other half will go to the oxygens. And then you subtract. So this is going to give me a formal charge of 2. All right, so now let's go to oxygen A. Oxygen A, oxygen, like sulfur, would normally carry 6 valence electrons. lone pairs count solely to that atom. So on oxygen A, I've got 6 lone pairs, or 6 electrons, 3 lone pairs. And then again, the 2 electrons in the bond, 1 goes to oxygen, 1 went to sulfur. So I've got 7 electrons assigned to that oxygen A for a formal charge of -1. Oxygen B. Oopsie, I was going oxygen B. Oh, how convenient. They're all the same. Oxygen would normally like 6. We've assigned 7 for a total formal charge of -1. And then I'm going to do this to all 4 oxygens. I get it. They're the same. I'll grab myself a little more room here. But I really do need to see all of these. Oxygen C, 6 minus 7. This is tricky math. And oxygen D would normally have 6 valence electrons. We've assigned 7 in our structure for a formal charge of -1. Does that make sense? How I got the formal charge on the oxygens? Normally 6 valence electrons. On each oxygen, there are 6 electrons in those lone pairs. Those count just for the oxygen. And then in the single bond, there would be 2 electrons shared, and we're going to split them equally. 1 went to sulfur, 1 went to oxygen. Cool. So we got all the formal charges on that first sulfate ion. Now, one of the rules was that if you add up the formal charge, you should get the charge on the structure, which we do get. If I add all these up, I get a -2. So this is a decent Lewis structure, right? Now let's try another one. Let's try this middle Lewis structure. On the sulfur, there'd normally be 6 valence electrons on the periodic table. That's the normal amount of valence electrons in a sulfur atom, minus the number that you've assigned in your drawing. We've got 1, 2, 3, 4, 5, 6. We've got like 6 bonds around that sulfur. We've got 2 double bonds and 2 single bonds. So that would really be a total of 12 electrons being shared around that sulfur. We split them evenly between sulfur and the oxygens. So sulfur gets 6 for a formal charge of 0. So every time there's a double bond, that's 4 electrons. 2 go to sulfur, 2 go to oxygen. Every time there's a single bond, that's 2 electrons being shared. 1 goes to sulfur, 1 goes to the oxygen. Ooh, I like this. Because I think we'd said too that, a stable structure is supposed to have low formal charges, zeros if possible. So now let's look at the oxygens. Oxygen A. Oxygen normally has 6 valence electrons. We've assigned him 2, 4. There's 4 electrons in those lone pairs. And then that double bond gets split. 2 electrons to oxygen, 2 to sulfur for 6. Formal charge of 0. Ooh. Let's try oxygen B. Oxygen B normally has 6 valence electrons. We've assigned 7 for a formal charge of -1. 6 electrons in those lone pairs. And then 1 electron from that single bond. 1 goes to oxygen, 1 went to sulfur. Now oxygen C and D are really just repeats. Oxygen C is the same as oxygen A. 6 minus 6 for a 0. Oxygen D is the same as B. 6 minus 7 for a -1. Okay, so this one's nice. Between the two, I'm liking the second structure better. They both give me an overall charge of -2, which is good because the structure has a charge of -2. But the second structure has lower formal charges. That's more stable. In a sense, it kind of means that we've assigned the amount of electrons, valence electrons, that the atom would normally carry. Okay, so now let's try this nutso one. Let's see what this looks like. Sulfur. Sulfur normally has 6 valence electrons. We're going to subtract the amount that we've assigned. 2, 4, 6, 8, 10, 12, 14. Awesome. we've given this sulfur, wow, 7 bonds, which would be 14 electrons. Half go to the sulfur, and the other half will end up going to the oxygens. Sulfur has a formal charge of -1. And now we do the oxygens. Oxygen A. Okay, this looks familiar. Oxygen would normally have 6 valence electrons. We've given him 7. Formal charge, -1. All right, in a second, -1. There we go. Oxygen B looks familiar. A double bonded oxygen. Normally has 6 valence electrons. We've assigned 2, 4, 5, 6. 0, I like that. Oxygen C, whoa baby. Normally has 6 valence electrons. We've given him 2 in this lone pair, and then the triple bond is 6 electrons that get split in half. So we've given this oxygen 5 for a formal charge of +1. And then finally oxygen D. Oxygen D looks just like A. 6 minus 7, formal charge of -1. Okay, so again, if the first part of a multiple choice question said, like A, B, C, D, which of the following is an acceptable Lewis structure? All of these are acceptable. Or if you had to draw them in a free response, these are all acceptable. But now if you had to rationalize which is most likely or which is most stable using formal charge, do you see which one is probably the best? This guy. They all have formal charges that add up to -2. That's a good thing. But we want low formal charges. That's always most stable. So that second one has the most zeros of any of these. There is 1 0 in that last one, but then I've got some kind of nutsy like +1s. That's kind of awkward. That second one is the best. Now, you might have a structure that has, the same amount of zeros as another structure. They both give you the same formal charge. They add up to -2. In that case, another thing to keep your eye open for, that negative formal charge should fall on any atom that has a high electronegativity, which we're going to look at in the next structure. So for now, I'm hoping that we're just kind of getting used to the most common trends or the common rules that you want to look for. Assigning the formal charge would be the number of valence electrons minus the number that you've assigned. We want low formal charges, meaning as many zeros as possible. We want them all to add up to the charge of the particle. And if there's any negatives, we'd like them to fall on the most electronegative atom.